send this to my notes. Hopefully we'll be good to go. Here it is. All right. So the first question says, when the velocity is at its lowest, what is the value of the acceleration? So that's like if you were to have, say, a spring or something, and it was oscillating back and forth here, you know, at the equilibrium, its velocity is at its max speed. But at its lowest speed, so say like over on the end over here, it wants to know what the value of the acceleration would be. So when the velocity is at its lowest, the acceleration would then be at its highest. All right, so the next question says, a 200-gram mass attached to a horizontal spring oscillates at a frequency of 2 hertz. At t equals 0, the mass is at x equals 5 centimeters and has a velocity of 30 centimeters per second. So it wants us to find a whole bunch of different things, and I crossed out some of them and replaced them with other things. For some reason, I can't really remember why I did all of that, but okay. You have to remember I made this like 2 years ago. So this first one wants us to find the period. So it gives us the frequency, so that's easy enough. We can just take 1 over the frequency, so 1 over 2 hertz is equal to 0.5 seconds. Okay, and the next one that I wanted you guys to find was the angular frequency, so just use the 2 pi over frequency since you have that information pretty easily. And then that should give you 4 pi radians per second. And then the next one wants us to find the amplitude. So this is one of those that we could use our energy equation because we have like our x value, we have a velocity, so we can find some information. And this one's a good one to find other additional information that we could, use some of those other equations with as well. So if we use this total energy equation, remember we did this one in chapter 15. It was like one of those examples. Might have been one like that you had on the homework that ended up being kind of an impossible answer to, if I recall. Okay, so one of the equations that you have for K on your equation sheet was like this. It was like angular velocity is equal to the square root of K divided by M. So if you rearrange to solve for K, that would give you angular velocity squared times mass. So if you plug in your angular velocity squared times the mass, which do we have? Oh yeah, the mass is 0.2 kilograms. Sorry. Anyway, that ends up being 31.5 newtons per meter. And then we can go through and take that information and solve for amplitude right here by rearranging. So if we rearrange this equation, amplitude is equal to 1/2 kx squared plus 1/2 mv squared divided by 1/2 k. You can cancel out if you want to, or you can just plug it all in. It'll end up working out the same way. You plug all of that information in and you should get about 5.54 centimeters. So you guys should pause and try to calculate that really quick and make sure that you guys get that for sure. And then the last one wants us to find the phase constant. So this is one of our favorite things to do, right? So phase constant, this is where you're going to want to use that one equation that just has the amplitude cosine of the phase constant, and you'll end up doing the inverse cosine of your x over your A. So you end up having inverse cosine of, what did it say was the x? It was 5 centimeters divided by your amplitude, which is 5.54 centimeters, which ends up giving you about 0.445 radians. Okay? All right. Now I think that I continued this on to find the other stuff that was listed before. So we still have the same bit of information, but now I crossed it out, and this is supposed to say over here max speed, max velocity. So you go through your equations, and you should see one that is for max velocity, which is just your angular acceleration times, or angular velocity, sorry, times amplitude. So go through, plug that in. You've got, I don't know why two arrows there. 4 pi radians per second times your, now your amplitude was in centimeters, so you could convert back over. It is possible that it would give you like an answer in centimeters per second, but just in case, this converts it back into meters per second for you. And then this next one is supposed to say max acceleration. So you have A max is equal to your angular velocity times amplitude. The amplitude again was 0.0554 meters, which is 8.8 meters per second squared. And then the last one is supposed to be total energy. So the total energy being 1/2 mv squared, or mv max squared. And so you've got 1/2 times that 0.2 kilograms times your maximum velocity, so 0.7 meters per second. And again, another reason why it's good to convert back to meters, because in this case, of course, you're going to end up with joules. So joules has to be in meters then. Okay, so again, I hope that you guys are sort of pausing through this and trying to work these out and getting the same answers. And if you're not getting the same answers, then of course you can message me. I do have, my mom had surgery yesterday, and I have surgery tomorrow on Friday. So I might not get back with you right away, but I will get back with you as soon as I can. So for the last one, it wants to know the position at 0.4 seconds. So you have to go through that position equation that gives you, that involves the amplitude cosine of that angular velocity. It involves the little time, not period. And it also includes that phase constant, since we did find phase constant. So we've got 0.0554 meters cosine. Use your angular velocity, which is that 4 pi radians per second. Plug in that 0.4 seconds, and this is really all in parentheses too. And then add that phase constant of 0.45 radians. And you should get about 3.8 centimeters. All right, so this should look familiar to like a problem that you would have seen on your chapter 15 homework. All right, next question. This one says that an object of a mass of 5 kilograms is attached to a massless spring and allowed to hang in the Earth's gravitational field. The spring stretches 5.4 centimeters before it reaches its equilibrium position. If this system is allowed to oscillate, what will be its frequency? Okay, so this is sort of like the part of the equations that have to do with like vertical oscillations. And whenever we were doing stuff with that, we remembered back to Hooke's law. So remember, Hooke's law was kind of like this. it had the spring force was equal to the negative K, or spring constant, times whatever that distance was. So first off, if we can just solve for K, then remember too that force is equal to mass times gravity. And then of course we're going to move the K over. So that's going to be like a negative, and so let's see, you end up with 5 kilograms times gravity divided by that negative 0.054, which when you move the negative back over from the K, then that ends up, being a positive then. It's kind of like this. So that negative from this K right here, which looks like an equals now, but that is going to go obviously to the other side so that K becomes positive. So you end up with a K constant of 907.4 newtons per meter. Okay, so that's kind of like the first step. Then you could go through and you could say, all right, what else can I find from this information? Well, let's see. Oh, we're trying to find frequency. So, maybe if you could find angular velocity, then you could end up finding frequency. So go through your equations. Okay, we've got one that has, angular velocity, and it has K divided by M in it. So we have K now, and we have mass. We just got to rearrange and solve for, the angular velocity. So if we do that, then we end up having the square root of 907.4 divided by 5 kilograms. So that ends up giving us an angular velocity of 13.5 radians per second. Then we can go back with this equation, solve for frequency. So we have angular velocity divided by 2 pi. So 13.5 radians per second divided by 2 pi. It's going to end up giving you 2.15 hertz. So, really good example of how you might have to use multiple equations. Again, why we have such a big equation sheet. I know. All right, last one in this section, and then I'll probably stop this video and have to start another one. So for this one, it says that a 0.05 kilogram block on horizontal frictionless surface is attached to an ideal massless spring whose spring constant is 190 newtons per meter. The block is pulled from its equilibrium position 0 meters to a displacement of 0.075 and released from rest. And the block is then in simple harmonic motion. When the displacement is 0.035, what's the kinetic energy of the block? All right. So it's wanting the kinetic energy of it. Okay. So we gotta figure out how we can find our kinetic energy of this. So we've got we could find the maximum kinetic energy by taking the total kinetic energy plus the potential energy. So we've got all of that information. If we can find the total maximum kinetic energy, then we could end up rearranging to solve for kinetic energy. So like this. Okay, so we've got 1/2 mv max is equal to our kinetic energy plus 1/2 kx squared. So go through some of that information that we've got. We could probably find some of that, right? So we've got, we could find the 1/2 kx squared pretty easily by just doing 1/2 times 190 newtons per meter times our x, which is 0.035 meters squared. And I don't really know what that equals. Is it 0.116 maybe? It got a hole punch in it from my paper. So let's calculate it. 0.116. Okay. And that is in joules. So all of the energy is still in joules. And then we're going to try to find the Vmax. So Vmax is your angular frequency times amplitude. And you can find the angular frequency again by doing the square root of k over m. So we've got the square root of 190 divided by the 0.05 kilograms, which ends up giving you an angular frequency of 61.6. And then you go back and solve for your Vmax. So you have 61.6 times that amplitude of, what is the amplitude? 0.075. And that ends up giving you 4.6 meters per second. So you can solve for that now. Got 0.05 kilograms times 4.6 meters per second squared is equal to 0.529 joules. And then if you go through and just replace that into this top equation, then kinetic energy is equal to your kinetic energy max minus your potential energy, so 0.529 joules minus 0.116 joules is equal to 0.42 joules. All right. So again, you've kind of got that energy principle equation again. All right, so I don't know how long this video is. I better stop it because YouTube doesn't like very long videos and start another one on the next section.